My name is Lukasz Kowalski, and I came from Politècnica University of Catalunya. And my physics tutor Jiménez is here also. So if you have any questions during the presentation after, we are welcome to answer you. And I'm going to talk about the low pressure anemometer for a space mission, and in this concrete situation for Mars. So this is the index of my presentation. We go from background to the modeling, simulation measurements, and I conclude my talk. So the objective of the work is quite simple: to have a modest sensor which would measure wind velocity and inclination number angle. The thing we want to underline is to measure 3D angle. So we just don't have a axial resolution in plane resolution, but you have full three-dimensional resolution. So why measure wind on Mars? Mars is a harsh environment, a lot of things is going on, and you need to have some in situ measurement in order to characterize Mars atmosphere. And another point is, if you want to send a man to Mars one a day, it's really nice to have good weather forecast. So to put in contrast Mars with Earth, you have like half-size planet with the lower gravity. But what is important for us is that the Mars pressure is roughly 150 times smaller than the Earth pressure, so it's a very thin atmosphere, and it's mostly done by carbon dioxide rather than nitrite and oxygen, what is in case of Mars. And the Mars is very cold planet. We observe very low temperatures. So we did some work for measurement wind on Mars. Our sensor is already within the Mars Science Laboratory mission. It's been done out of silicon dies. You see here 4 silicon array of the 4 silicon dies, and this sensor was 2-dimensional sensor. So in order to have a 3-dimensional readout, sensor was multiplied 3 times around the boom, and the 2 booms looking in the orthogonal direction were placed and situated in the upper side of the rover mast. So when the whirlwind comes over the rover, our sensor, 4 of the dice, noticed some disruption in the lecture. So this is the proof that the sensor is measuring itself. So now, thinking about 3-dimensional model, encouraged by the previous design, we thought that it's gonna be nice to have 3-dimensional symmetry, and we propose a spherical figure. So our sensor now is not gonna be a planar as it's been before, but we propose the hot sphere. So you see when the wind comes across the hot sphere, some heat is conducted by the phenomenon. So basically, the sphere is kept at the constant temperature higher than the flow temperature, and the structure is sensitive to the wind velocity, and it's not sensitive to the direction. So it doesn't matter when the wind comes from. The readout, the convection parameter is always the same. The reason why we choose also sphere is really known. Our simulation are in agreement with the common known empirical model. You can see here that when the wind goes up, the convection heat follow the empirical curve. Okay, so now our sensor is gonna look like that. You will have the external thrust, support, and the central core. The reason why we introduce a central core, I will show you just in a moment. So in order to keep the sensor at a higher temperature, you need to provide some heat. This heat is I denominated it as a surface heat. It's a sum of the conduction to the center of the core, radiation, and the convection parameters. So when we keep core at the same temperature as the external surface, we just reduce the conduction losses. We plan to polish external surface to the mirror finish look like and put some gold thin film just to diminish the emissivity factor. So the radiation heat also gonna be more or less zero. So whatever stands is a convection, and this convection depends on the thermal conductivity of the surface, and this is exactly product of the velocity. So therefore, our sensor monitoring the power we deliver to the surface, we will be able to extract the velocity of the wind. You need to know when the wind comes across the sphere, it goes very smoothly in the front of the sphere, but at the end of the sphere, some vorticity is being produced. So in order to have this vorticity axis symmetric and stable, we need to keep our Reynolds number below the parameter 210. It's why in the previous presentation I've been asking about the Reynolds number. So as you see here on the graph, when the Reynolds number is presented as a function of the sphere diameter and velocity factor, so if we want to measure up to 10 meters per second, and we need to choose a very nicely sphere diameter just to be below the 210 number. So we are working now with the 11.2 diameter of the sphere just to have this symmetry. So from the console simulation, we put a sphere into a Mars-like flow condition, and when the wind comes across the sphere, so it's kept at the constant temperature, you see some distribution of the local convection coefficient. So providing that the Reynolds number is less than 210, we see that all of the points of the sphere depends just on the zenith angle, which is the angle of the incidence wind direction and the any point of the sphere. So for every point of the sphere, when the zenith angle is the same, it's gonna be this circumference, you have exactly the same local heat coefficient, and it also can be seen from the graph that the convection factor is higher in the incidence point and going down to the rear part of the sphere as it's shown from this graph. So we think that from that part we know that the doing integration over all sphere, we can easily have the wind direction measurement, but when we divide sphere into sectors, we still can have a wind velocity measurement, just making a sum of the factors. But from the partial measurement of each sector, we think and assume that we can be able to measure the wind direction as well. So we done some simulation, and here you have a sphere, the simplest division in the two hemispheres. When you move in the horizontal axis from the point 0, 90 and 100 degrees, you will see that the thermal conductivity of the hemisphere will be decreasing, and it is for all velocity, for all different velocities. And whereas we notice a decrease in thermal conductivity of the hemisphere A, hemisphere B being in the rear, is going from the lower part to the higher part. So we have like variation in the thermal conductivity of each sector, whereas sum is maintained constant. So now is the time to introduce our prototype device. So our prototype is made of, we use a platinum sensor in order to check temperature of the hemisphere at the hot temperature, and the platinum is also used for the temperature monitoring, as the platinum linearly depends on the temperature. The external shell are produced out of silver in a stereolithography method. You see some shape inside the silver. These shapes are providing us a good contact with the platinum heaters, and there's custom PCB made to sustain the structure, and you can observe internal core in the center of the PCB. That core, from the infrared image, you can see when the core is operating, you have heat delivered to the middle of the structure, and finally, the structure, once assembled, I remember you, the diameter of the structure is 11.2 millimeters. Okay, now when we have our prototype, it's time to do some measurements. Unfortunately, we don't have a facility which enables us to go to the chilling Martian range of temperatures. It's very low temperature, and also we wanted to work with the toxic carbon dioxide. So we come up with idea to match some dry air parameters and laboratory temperature to have the same sensor behavior. So when we match the Reynolds numbers, Nusselt numbers, and power convection factors, we find out that doing the experiment in 24.5 millibars of the dry air and with the laboratory temperature, we will have much more the same result within the 2% of error for the one hemisphere when we move the incidence angle from the point A, from the point of 0, up to 100 or 360 degrees you go around. So once we know that we will expect the same answer of the sensor, we put our sensor inside the low pressure chamber. We establish the atmospheric pressure, and we start our measurements using a desktop wind tunnel inside the low pressure chamber. So this is a slide you've been probably waiting for all presentation. These are the measurements and the low pressure. Our sphere is being rotating in the way that the wind incoming jaw angle is being changing from minus 60 to 240 degrees. You observe that one of the hemisphere changes its readout, and the other. Oh, sorry. I know what's going on. So the one of the hemisphere A, is changing the heat power delivered to the hemisphere, is changing its value. At the same time, hemisphere B also changes the value, but the sum of those is maintaining a constant level. It's the convection power, 100 milliwatts. Whereas the power delivered to the center, to the core of the was about 18.6 milliwatts. So we did the same experiment for three different velocities. You can see from the graph that the answer of the sensor is quite similar have a similar shape, although the sum of the power is changing in a piece as we change our velocity for the sum. To put in conclusion, we think it's a good candidate for the Martian atmosphere wind measurement because it's compact. You have this protective shell, external shell, it's well behaved. We observe the laminar flow behavior. It's efficient. We can estimate velocity and the angle of the coming wind. So the next step is gonna be expand our structure from the two hemispheres to 4 sectors. As I said you before, just 2 hemispheres enable us to measure in the semi-planar surface, but a full tetrahedral shape of the 4th sector will enable us to have fully 3D measurement of the wind angle, and this structure also shows very high and homogeneous sensibility for any wind incidence angle. Thank you for your attention, and I please ask you the questions.